Welcome to a short introduction into modern electronics production technology. My name is Leif Halbo, and my task is to guide you through this video. It's my hope that you will find the briefing helpful in understanding the various technologies that we will discuss, and that you will enjoy the next 25 minutes of this tape. You are going to see three different production methods. First, printed circuit board or PCB production, then thick film hybrid circuit production, and finally production of thin film hybrid circuits. To illustrate the three methods, three fine Norwegian electronics companies are chosen to show us the details of modern manufacturing of electronics. Let's take a look at the most common production technique, the use of printed circuit boards with bowl and surface mounted components. To illustrate manufacturing of modern printed circuit boards, we shall concentrate on two specific products. One is an intelligent computer terminal, and the other is a high-speed cassette tape recorder for computer backup called Streamer. Inside the Streamer, we find two printed circuit boards, one thick film hybrid circuit, and several custom design integrated circuits. In order to save board area and rationalize the production, the two printed circuit boards are produced together and finally separated at the very end of the process. The computer terminal is a more complex product with 6 printed circuit boards and the cathode ray tube. Tandberg Data outside of Oslo, Norway, has a modern, high-volume production line for these products. At peak production, Tandberg Data makes 1,300 streamers per day. This is possible because of a high degree of automation. Up to 96% of the work is done automatically. Only a few of the 730 employees are needed to supervise the just-in-time production. Statistical process control is also used to achieve Tandberg Data's goal of 6 sigma quality. This means that there will be less than 3.4 defective parts per 1 million delivered. For the Streamer, Tandberg Data has chosen to use pure surface mounting for the main printed circuit board and to have all the components on one side. Let's follow the production of this printed circuit board. In surface mount technology, we normally supply the solder by screen printing of a paste containing tin lead particles mixed with solder flux. The printer and the metal printing stencil are easily recognized. The stencil has a small opening for every solder pad where we want to deposit solder. During the printing, a rubber device called squeegee pushes a heap of solder paste across the stencil, and a small amount of paste goes through every hole and is left on the printed wiring board underneath. The main types of surface-mounted components are resistors and capacitors with small rectangular-shaped bodies, discrete diodes and transistors, small outline packages, plastic leaded chip carriers, flat packs, and leadless ceramic chip carriers. The next step is the mounting of small passive components and transistors on the already deposited solder paste. This high-speed pick-and-place machine can mount up to 10 to 15,000 of these components per hour. Tape reels are used to store the components. The machine has a number of vacuum tools and is programmed to find the right component and then mount it on the correct spot on the board. The positioning can be watched in detail on the TV screen. Placement accuracy is 0.1 millimeter for 4 mils. After placement of these components, the boards automatically move to the next machine, which mounts the large ICs. Even these are delivered from tapes. This machine works in a slightly different way. It has two separate pickup heads programmed to move in the X direction, and the board can move in the Y direction. The principle of reflow soldering is to heat the solder paste to its melting point in a carefully controlled manner. This soldering machine operates with infrared radiation for heating combined with hot air. It takes some 10 minutes for a board to pass through the machine. Inside, heater elements above and below heat the boards slowly in the beginning to dry the solder pastes and activate the flux in it. Near the end, the solder alloy melts at about 180 degrees centigrade. Hole mounting is still of great importance. Such mounting is used for Tanbur Data's computer terminal boards. There are three common types of hole components: axial, radial, and dual inline integrated circuits. We'll start with the axial components. The axial components are supplied in paper tapes on reels. It has been found practical to remove the components for a particular board from their tapes and mount them in a suitable sequence into a new tape. The machine doing that is the sequencing machine. Each section of the new tape has all the axial components for one board. The plain board is ready to be filled with components from the sequencer tape. The axial insertion machine does this. It cuts the leads to suitable lengths, bends them at 90 degrees, and inserts the axial components into the appropriate holes in the board. The radial insertion machine places large capacitors and other hole-mounted components with leads coming out parallel. All component tapes are stored in this machine without sequencing. Dual inline components are normally received in long plastic sticks. The dip inserter has all types of sticks in its magazine. Although around 90% of the components are placed automatically, we need a number of operators mounting odd parts by hand. These parts are special capacitors, transformers, connectors, etc. Some of them are hand soldered as well. An alternative to hand mounting of odd-shaped components is to mount them by a flexible, programmable robot. This robot mounts some of the keys for the keyboard of Tanbur Data's terminal keyboards. The robot does not appear to work very fast, but once it is properly set up, it works continuously and very reliably with little attention. Now, after automatic insertion and manual placement of odd components, the board is ready for wave soldering. The foam fluxer sprays flux mixed with air onto the lower surface before the board passes the 120 degrees centigrade heated zone. At this preheat temperature, the flux is activated and volatile solvents evaporate. Next, the board passes a wave of molten solder metal at a temperature of 240 to 260 degrees centigrade. The solder metal wets both the component leads sticking out of the board and the copper foil solder lands around the leads. When the board comes out of the wave, the solder remaining on the board solidifies and the joints are soldered. Testing of the product is done at several stages and in various ways. It can be a functional test with contacts to the normal circuit terminals, or an in-circuit test where every component is tested by being contacted by a test fixture called bed of nails. In this case, a combination is used, testing the main functions of the board, as well as in-circuit testing of some critical points and components. Our visit to Tandberg Data has come to an end. There is much more to be seen and to be discussed in high volume, quality, design and production, but our time is limited and it permits us only a taste of the essentials of PCB production. Let's then take a look at the second issue, thick film hybrid circuit technology for making high reliability compact electronic circuits. The Norwegian company Microcomponent is a specialist in thick film hybrid circuits. Ernest Skåntorp, the company's managing director, has a team of 40 employees which make thick film hybrids for a multitude of applications. Let's follow the manufacturing of this thick film hybrid, which is one of the major components in a sonar made by Simrad Subsea. It analyzes the echo signals reflected from objects in the water. The detailed design takes place in the computer-aided design station, which provides information to various production stages, testing, component purchasing, etc. The first task is to fabricate the hybrid substrate with multiple layers of conductor patterns, insulation, and integrated resistors. The substrate base material is an aluminum oxide or alumina ceramic plate, 10 × 10 centimeters in size or 4 × 4 inches, containing 12 circuits that are processed simultaneously. The various circuit materials are deposited on the ceramic substrate by screen printing. The screen itself is made of thin, woven stainless steel wires and is masked by a photosensitive organic film. The first step is printing of conductor layer number 1. After printing, the drying process takes place. The furnace heats the circuits to 150 degrees centigrade for 10 minutes. The volatile components of the printing paste evaporate. The cassette is necessary for subsequent automatic handling. In this furnace, the printed layer is cured or fired for another 10 minutes at a temperature of 850 degrees centigrade. Organic filler material in the printing paste evaporates. The glass particles in the paste will melt and make a very stable matrix for the conductive metal particles. The metal may be a silver palladium alloy, and the conductor will be about 15 micrometers thick after firing. In order to insulate these conductors, a new layer is screen printed, this time with an electrically insulating paste. Contact holes in the insulating layer make it possible to join conductor layers together electrically. In our circuit, we'll need 4 conductor layers. The printing, drying, and firing processes are repeated for each conductor and insulation layer. Each time, different printing masks are used. Resistors are also added by screen printing. They are made on the reverse side with electrical contact through metallized holes in the substrate. The geometrical shape of the resistors and the concentration of metal oxides in the paste, like ruthenium oxide, will determine the resistance. The available values range from 0.1 to over 100 megohms. A powerful laser removes tiny areas of the resistor. This makes it possible to achieve accurate adjustment of the resistivity. A measuring instrument connected to probes automatically tells the laser to stop cutting at the desired values. The precision is down to 0.1% in absolute trimming. Our substrate is complete and ready for surface-mounted components. Like on surface-mounted printed circuit boards, solder is again applied in paste form by screen printing. Pick-and-place machines similar to those in printed circuit board production are used. 120 different components are picked from the tape magazine in this machine with a speed of 3,500 devices per hour. Passive devices, diodes and transistors are measured during placement. Components outside of specification are discarded. Integrated circuit packages are carefully aligned for accurate placement. After component placement, the circuit is heated in a furnace for reflow soldering. The solder paste melts and then solidifies. Cleaning of flux residues completes the process, and the substrate is ready to be broken into individual circuits. At last, external terminals to the circuit are provided by soldering single inline leads onto the substrate. A very important step is the test of performance. Careful visual inspection is followed by an in-circuit electrical test. The circuits are ready to be shipped. Electrostatic discharge protection is provided by anti-static plastic bags. The last topic to be covered is thin film hybrid technology. Thin film hybrid circuits give us a very high packing density and excellent high frequency properties. They provide superior reliability in hermetic encapsulation and are found in a wide range of applications, like for example in this device. The cylinder is a part of a system used to collect seismic data for oil exploration offshore. A ship towing several cables with attached cylinders sends intense acoustic pulses. The reflected signal is picked up by these cylinders, and inside each cylinder we find very complex electronics, including 24 thin film hybrid circuits. To get the highest possible packing density, a folded flexi-rigid board is used. Let's take a closer look at one thin film hybrid circuit. It contains 2 custom-designed silicon integrated circuits, many naked standard circuit silicon ICs, several thin film resistor networks, and surface-mounted device capacitors, all mounted on an alumina ceramic substrate. The housing is a hermetic metal box with a metal lid. The electronics in the cylinder is manufactured by a Norwegian company named Getec. Hans Paulsson, the technical manager, will show us the production of one thin film hybrid. In thin film hybrid technology, a pattern of conductors is etched out of thin layers of metallization. This pattern gives interconnection between components on the substrate. Like in thick film hybrid technology, resistors can also be made as part of the substrate, but the layers are thinner, normally less than 2 micrometers. In standard thin film hybrid technology, the substrate has an upper layer of conductors and a lower layer of resistors. The lower level is made of nickel chromium, which gives a relatively low conductivity. The upper layer of conductors is made out of gold, giving very good conductivity. To improve the adhesion for the gold layer, a very thin layer of titanium is deposited between the nickel chromium and the gold. The metallization is done by vacuum evaporation or sputtering. However, to reduce the costs, Getec purchases the substrates with uniform layers of metallization instead of doing the deposition in-house. The definition of the different metal patterns is done by a photolithographic process. In the photoresist spinner, a few drops of photosensitive liquid, called photoresist, are deposited in the center of the substrate. Then the substrate is rotated at high speed, and the resist spreads out to a thin, uniform layer covering the whole substrate. The yellow light in this room does not affect the photoresist, and the operator wears special clothing to prevent dust particles from contaminating the surface. A sheet of glass bears a metallized stamp of the conductor pattern and is placed on top of the substrate as a photomask. The substrate is now ready to be exposed by ultraviolet light through the photomask. During exposure, the conductor pattern is copied onto the substrate. The developing procedure removes the exposed photoresist and leaves behind a protective layer of unexposed photoresist on the conductor pattern. Now, we are ready for the chemical etching of the gold metal layer. The first etching bath consists of a mixture of potassium iodide and iodine. This mixture dissolves gold, but not the protective photoresist, nor the titanium. The titanium is etched in a second bath, which contains hydrofluoric acid. Then the substrate is rinsed with water. Definition of the resistor pattern requires a new photolithographic step. Photoresist is again deposited, and the substrate is exposed through a new photomask. Then the nickel chromium layer is etched in a bath of acetic acid and ammonium surnitrate. The next step is to mount components. Integrated circuits are mounted in bare chip form. The silicon chips are glued onto the substrate in the so-called die bonding process. A drop of epoxy adhesive is applied for each chip. Capacitors are also glued. In this case, the adhesive provides electrical contact as well as mechanical support. The adhesive is cured at 165 degrees centigrade for about 2 hours. For silicon chips, electrical contact is provided by gold wires down to 25 microns in diameter. The bonding machine automatically makes the connections. Wires are pressed down to the bonding area of the chip at elevated temperature and with ultrasonic vibration. Then they are pressed against the corresponding bonding area on the substrate and finally torn off. This is called thermosonic bonding. Just like the process we saw in the thick film part, laser trimming is used, this time active. Resistors are trimmed to give the desired gain of an amplifier, zero offset, or the appropriate frequency response of a filter, etc. A hermetic metal box protects the thin film hybrid circuit. Before this encapsulation can take place, the circuit needs to be dried overnight at elevated temperature. No moisture is allowed. In this chamber, the metal lid is mounted hermetically by resistance welding after the ambient air has been replaced by dry nitrogen. An essential step is the extensive testing of the circuit. The test is made at -10 degrees centigrade and at +65 degrees to verify operation in extreme environments. The thin film hybrid circuit is finished and ready to be mounted on the printed circuit board of the seismic data collection system. This brings us to the end of this program. I hope you got the essentials of the three technologies that we have discussed: printed circuit board, thick film, and thin film. If not, you might consider watching the tape once more. I'm Leif Hallbo. Have a nice day.